guys see my course web page on the background? Let me go to the, can you see it?
Yes.
All right. So in the module 0, when I click on that, this August 17 Zoom class meeting video, Introduction to Course and Chapter 1, I have put a link in the Canvas web page so that you can go back. Okay. So we were talking about Chapter 1. We were going over Chapter 1. Matter, energy, and measurement. So we talked about generally about chemistry and then about scientific method, and we were studying about measurement. So I'm going to continue the chapter 1 from there, where I stopped last time. Okay? Do you guys have any questions?
No.
All right. Let me see whether I can expand it. All right. We talked about introduction to chapter 1 and talk about chemistry, how we study matter, chemical changes and physical changes, scientific method, we talked about it. And I told you why measurement is important to scientific method. Observations are the first step in the scientific method. So we're going to look into observation, which include measurements in detail. Now, a measurement could be quantitative or qualitative or quantitative. Qualitative is just a statement. This car is faster than the other. Quantitative means this car travels 5 miles, other car travels 10 miles. So measurement have a number and unit. There are 6 base units in the metric system. We talked about that. Important part of the measurement is number. Number is expressed in scientific notation to make it easier to deal with large numbers and small numbers. We go know it. Now, you should be able to convert scientific notation to normal form. You move the decimal place. So we talked about that. These are the 6 base units in the metric system. They are meters, liters, grams, seconds, Kelvin, and moles. There are other systems of units, CGS system, where centimeter, grams, seconds are used. The common system, day-to-day use, we use pounds, gallons, etc., and Fahrenheit. Okay, when you look at unit part of the measurement, it could be abbreviated or expanded. a small amount number in the measurement with a lot of zeros in the decimal place. So we can use kilograms or micrograms rather than just using grams. So this is scientific notation applied to unit system. So we gone over this little bit. Okay, that's where we stopped last time. How many of you remember we were there last time? Can you guys hear me?
Yes.
All right. I'm just checking whether my mic is working. Okay. If you have a measurement, which is important in scientific method, it has number part and the unit part. Now we're going to look into a unit part, a number part, and show how we round off, how we tell significant numbers, significant figures in the measurement. First one, if you have a number with no zeros, all numbers are significant. 233.1. All four numbers, the last number to the right is the uncertain digit. Uncertain digit is 1. You count all the digits, numbers, starting from uncertain digit to the left. 1, 2, 3, 4. So this number 233.1 has 4 significant figures. Pretty easy to find out the significant figures when there's no zeros. Zeros complicate. We're going to look into how we do it when there's zeros. 2.3 has 2 significant digits. Starting with 3, there are 2 numbers. 3 in the 2.3, right most number is 3, which is the uncertain digit. So we normally, in a measurement, we round off it to the uncertain digit. So measurements are just not all the numbers. Only we write down significant numbers, which are important. Okay, about the zero, when there are zeros, in leading zeros, zeros at the beginning is called leading zeros. Now, paragraph 2. For example, 0.0055. The leading zeros are not significant. Any leading zeros in a number is not significant. Do you understand? It's a whole number. We don't write zeros. In decimal numbers, we have to use numbers to show the zeros, to show the placement of decimal point. Okay, leading zeros are not significant. You understand that? Paragraph 3. 0 at the end of number, which are called trailing zeros. In a whole number, trailing zeros are not significant. But in a decimal number with decimal points, zeros are significant. For example, 3.00, 2 zeros at the end are significant. Therefore, both zeros count for the significant figure. Therefore, 3 significant figures. On the second example, 0.0450, the beginning two are leading zeros. They are not significant. But the last one on the right, after 45, is in the decimal place. Trailing zeros in the decimal place. Therefore, it's significant. Therefore, three significant digits. So zeros at the end of the number that contain no decimal place may or may not be significant. So, for example, $36,000. There are three zeros. Is ambiguous. Therefore, we normally consider as two significant figures. If all zeros are significant, you have to put a decimal point at the end of the number to make all five numbers significant. Okay, if you take 5.00 milliliters, only 5,000 milliliters. That's a comma after 5. So only first number is significant. Therefore, it contains one significant figure. But to make all the significant numbers significant, you have to put a decimal point after 500 decimal point. That makes it significant figures. Now you got some idea about how we figure out significant figures on given numbers. Any number with some with the trailing zeros, leading zeros, some with decimal points. Okay. Do you have any questions about this?
No, sir.
All right. If you have, we can talk about it later. Okay. Now I have to tell you about certain numbers which don't have significant figures. They're exact numbers. For example, if a number comes out of a definition, 1 dozen is 12 is equal to 12. 1 dozen is equal to 12. 1 egg is equal to 12 eggs. That's a dozen of eggs. So those numbers 1 and 12 are exact. There's no significant figures in them. So when we use them in calculations later, we don't look at their significant figures. All right? I'm going to bring that point later. What is the exact number? Exact number is one found in unit conversion factors that comes from a definition. 1 centimeter is equal to 15.3 centimeters, or exact number results from measurement of observation and contain some uncertainty. Okay, we are going to talk about what exact numbers don't have significant figures. Okay, can you remember that? Exact numbers which are found in conversion factors don't have significant figures. We're going to go through some examples again. First number, 65.2. there are three significant figures. Why? You count the 2, that's the uncertain digit, and count from right end to the left, 1, 2, 3 figures. The next number, 255.345. has 6 significant digits. You see, rightmost 5 is the first one, then you count to the left, 1, 2, 3, 4, 5. 5 digits, 6 digits. Okay, that's how you tell a significant figure. Okay, these are examples of that I try to explain in a previous slide. In 0.00245, how many significant digits are there? The zeros are at the beginning are called leading zeros. They are not significant. Therefore, you don't count them. Therefore, 5, 4, 2, only 3 count for 3 significant figures. The next problem, 0.008. Leading zeros are not in the decimal place, are not significant. Leading zeros in whole number also not significant. We don't write zeros in front of 200. You don't ever write. So that's, you also already know not to write. But in decimal places, you have to keep the place value with zeros. Okay, third one, 2,570. So normally that 0 at the end of a whole number is not significant. Therefore, it's 3 significant figures there. If you want to make that 0 significant, you have to put a decimal place after 0. If I had 0 after this decimal place here, decimal point there after 0, it becomes 4. But none of these have. Okay, this is the whole number. These 2 zeros are not significant. Therefore, it's only 5 significant digits. Do you have any questions about it?
No, sir.
No, sir.
All right. Thank you. Now we're going to talk about measurements. When you use measurements with number and the unit in calculations. In calculations, when we use measurements, you can either add them or subtract them. Also, you can multiply 2 measurements or divide 2 measurements. All right? So the question is this. When you add or subtract 2 measurements, the answer also should have an uncertainty and significant digits. So in addition and subtraction, if you do a calculation after you do the measurement, for example, 2 numbers, 10.11 kilogram and 3.6 kilogram. When you subtract, do a calculation, subtract these 2. The number you get is, in calculator you get is 6.51. Is it 6.51 correct measurement with correct significant figures? Of course, it's not. So when you add in 2 numbers or subtract in 2 numbers, you have to look at the number and first number, decimal places in the number. First number, 10.11, the rightmost decimal place is second decimal place. In 3.6, rightmost decimal place in first decimal place, second decimal place, first decimal place. If you look at these two numbers, measurements, uncertainty in the second decimal place is lower. Uncertainty when you have the number at the uncertainty in the first decimal place, uncertainty is more uncertainty in first decimal place than in second decimal place. More uncertainty as you move, less uncertainty as you go to first, second, third. Third decimal place has lowest uncertainty. First decimal place has most uncertainty. So we use that fact to figure out where the uncertainty is in this added number. Uncertainty should be highest uncertainty. It should be in the 5 because highest uncertainty is in the first decimal place, which is the 6th and the second number. Therefore, this number has to be rounded off to first decimal place. How you round off 1 to 5? If the number to be dropped to round off is 1, it's less than 5. If one number to be dropped is less than 5, you just drop it. So number becomes 6.5. When you add and subtract, in this subtraction, the significant number, the answer with the final answer with the correct significant digit in the first decimal place is 6.5 because 6.5 is the lowest decimal place of the two numbers which has lowest decimal place. So that decimal place is carried on to the answer. Now, how many of you understood it? Do you have any question? When you add and subtract, you add the number and round out the answer to the decimal place, which is to the most right, most left. 6 is more to the left than 1 in the last decimal place. All right? Do you have any questions about this? Okay. When you do addition, it's the same rule. Now, when you do two measurements, use two measurements in a calculation where it is divided here. 351.2 divided by 5.5. Do you see that? The calculator answer you get is 63.854545. If you plug in your calculator, you get the number. You are calculating speed of a car or object. So to calculate the speed, you have to use miles and hours that took for the car to travel. So how you get the significant, how do you get the number rounded off to correct significant figure is this way. In addition and subtraction, you look at the decimal places. You don't look at significant digits. In multiplication and division, you look at significant figures. The first number, 351.2, has 4 significant digits. Second number, which you divided, 5.5, has 2 significant digits. the answer 63 should be having two significant digits, because the two significant is the lowest. Like the uncertainty in the decimal place is the lowest significant figure. Therefore, number should be rounded off to this 8 should be dropped, and 3 should be, you have to drop all these. When you are dropping it, the number next to it, next to 3 is 1. If the number next to the one that you going to add to greater than 5, you add a 1 to 3. Therefore, correct answer is 64. So we look at in detail about this. This is the same answer. The numbers to be retained is 63, two places. 8 is the number to be dropped. Along with 8, you drop all other numbers to the right. Therefore, 8 is greater than 5, between 5 and 9. Round up the last digit to be retained by 1. Last digit to be retained is 3 here. So it becomes 64. Now, how many of you got the idea that when you do calculations, you have to follow the significant digit or lowest decimal place in addition and subtraction to get the correct answer in the calculations? All right. So this is important. All right. Now I am going to talk about conversion factors. Conversion factor is here, 2.21 pounds, which is in the middle, is equal to 1 kilogram. A conversion factor is something that we use to convert pounds to kilograms or kilograms to pounds. So if you start with pounds here, you use this conversion factor in two forms. This conversion factor could be used as two fractions. Pound on the top, kilogram on the bottom, kilogram on the top, pound on the bottom. If you start with pounds, you have to have the pounds at the bottom. So conversion factor is this one. Then you get the desired pounds and the number. You do the number. When you're doing the calculation, these are exact numbers. Remember I talked about exact numbers which don't have significant digits. Therefore, they are ignored in considering significant digits in the answer. All right, let's go finish it up. Now you need to convert 130 pounds into kilograms using factor label method. Units are treated like numbers. Make sure all unwanted units cancel out. The pounds should be cancelled out with the units in the conversion factor. So what conversion factor we said we use for this conversion? 1 kilogram divided by 2.21 pounds. Okay. So in the next slide, We gave you two choices. This is the first conversion factor where the pound is on the top. Second one is kilogram is on the top. To cancel this pound in 130, you need to pick the conversion factor where pounds is at the bottom. So when you do that, you get 59. Why 59? You don't consider 1 or 2.1 to the significant figure. This is the multiplication through this. This 130 has two significant digits. Therefore, number should have been rounded off to 59, which is two significant digits. The bottom conversion factor has original unit in the denominator. Denominator is the fraction, bottom part of the fraction. The unwanted unit is pound, cancels. These LBs, pounds, cancel out. The desired unit does not cancel out. Kilograms goes into the answer. So you do the calculation. Do you have any questions? Are you guys okay?
Yes, sir.
All right. Now we're going to talk about a little bit of mass, difference between mass and weight. Mass is the one we use in sciences. Weight is one we use in different places. Weight is affected by gravity. So I will be heavier on Earth than on Moon because gravity is less in the Moon. So therefore weight depends on the place where you live, high elevation or whatever it is, in a different planet. Mass is fixed. Mass is measured using a balance. You have to have a standard weight balance where you balance out standard weight to the weight you are measuring. So weight is measured by a spring balance. Spring balance is one that pulled by the gravity. There's no comparison to another weight in there except the calibration. Okay, mass is independent of the location. Weight is affected by gravity. Weight depends on the position. Therefore, what we use in the sciences, mass or the weight, we use mass. Sometimes we call it weight, that means it's mass. Okay, sometimes we use weight word with the opinion that it's same as mass. One other basic measurement is temperature. Temperature is measured in 3 scales. Fahrenheit, which is you are familiar with. Celsius is second one. Kelvin is third one. How do you convert Celsius to Fahrenheit? I have underlined here. You take the Celsius temperature, multiply it by 1.8, add a 32, you get Celsius converted to Fahrenheit. To go other way around, Fahrenheit to Celsius, you undo what you've done in the Celsius to Fahrenheit. You take the Fahrenheit value, subtracted 32, now 1.8 divided by 1.8. So therefore, if you remember this first equation, you can always get the second Fahrenheit to Celsius. It is the reverse of that, 1.8 fraction Fahrenheit minus 32. Celsius to Kelvin scale conversions are pretty straightforward. Celsius added up 273.15 exactly. This is rounded off to 273. If you add 273, Celsius become Kelvin. How do you undo it? You subtract. Therefore, these first two conversion factors, you can do backwards or forward, all right? So you need to remember this, okay? So we will be doing conversions of temperatures. Now about if you do a numerical calculation, 1.8 and 32 or 273 are all exact numbers. Why? They are coming out of definition. Therefore, you only consider the significant figure in the Celsius or Fahrenheit or Kelvin or scale. When you don't think 32 or 1.8 in the significant figure calculation. They are exact numbers. Now, how many of you got the idea that exact numbers are not, comes out of a definition, are not using the calculation? All right. Now, where does that 1.8 come from? Conversion factor. You had multiplied Fahrenheit to, in this case, Celsius to Fahrenheit, 1.8. 1.8 comes out of divisions in the Fahrenheit and the divisions in the Celsius. 0 to freezing point to boiling point in Fahrenheit scale is 180 scales. 32 minus 212 minus 32 is 180. In the Celsius scale, 0 to 100, that's the 100 scale. Therefore, Celsius calculation, you have to divide 180 by 100. 180 divided by 100 is 1.8. That's why we multiply Celsius by a factor of 1.8. That's where it comes from, scale changes. So 32 is shifting the scale. You have to shift up for the, you add a 32 in the equation. Do you have any questions about how we use conversion factor equations in the converting Celsius to Fahrenheit, Fahrenheit to Celsius, Kelvin to Celsius, Celsius
No,
to...
sir.
All right, good. There are many conversion factors. I have listed them on this table. None of these numbers have significant digits. They are exact numbers. Do you understand what I mean by them? When you do calculation involving them conversions, you don't look into their uncertainty. Only uncertainty comes from one with the measurement. All right? So you will figure that out when you do the problems. When you use a conversion factor, you don't look into their significant digits or uncertain digits. We gone over this, converting pounds to kilograms. So I put it again here. This is 130 pounds converted to kilograms. We pick the bottom conversion factor, 1 kilogram divided by 2.21. Got the 59 kilograms. So we go know that. Now doing calculations using conversion factors are called factor label method. Conversion factor, a ratio of two different units used as a multiplier to change from one system to the another unit. How you change grams to pounds. You look in the table here, which I given you in here. Where is that? This one. 458 grams is a 1 pound. You can use that. I'm not sure it's the same thing you have. It could be other way around. 453. So it depends on the value is given. 453. 454 is rounded off there. It doesn't matter. 454. It doesn't count for the whatever the value that you were given in the problem has to be used. Therefore, 453.6 don't have significant digits. They are exact numbers. So when you do the calculation, in this case, using 453.6, you get 0.840 as the answer. So it's rounded off to 3 significant digits. Why? 381 has 3 significant digits. 4.840 also has 3 significant digits. So that's correct. So not only you can use one conversion factor in a row. First this conversion, gallons to liters. You have to calculate the milliliters. Then you use a second conversion factor. 1 milliliter is equal to 1 liter. So if you look at the, probably it's there. They don't give, this is prefixes in the units. What is a milliliter? Milliliter is 1,000 liters. 1 liter is 1,000 milliliters. So you know it from the prefixes in. Therefore, you can convert gallons to milliliters using 2 conversion factors. All these numbers in the 2 conversion factors are not significant. Therefore, answer should have 4, only 4, because 1.844 has 4, 69.80 has 4. All right. So we done with the number and the unit part of the calculation and how we use them in calculating using certain measurement. Get another measurement which are coming from your measurements. So calculated measurements has to follow uncertain or significant digits in the measurements. And they also have certain uncertainty based on uncertainties of the original measurement. All right. We're going to shift the gears here and go in the direction of chemistry, definition of matter. Okay, we told you before, matter is anything that has mass and a volume. That is the general definition. But according to the chemist or chemistry, matter is either composed of atoms, molecules, or ions. All matter made up of atoms, molecules, and ions. We didn't write ions because ions come from losing or gaining electrons from atoms. The way that atoms and molecules combine and different combination of atoms and molecules create two categories, the way atoms and molecules combine. Atoms and molecules, atoms combine to create pure substances. Do you see substances there? What is a substance? It could be either element or a compound. All matter which compose atoms and molecules could have complex mixtures of substances. So they could be mixtures of elements and compounds. Therefore, on the right side, you have mixtures. On the left side, you have substances. So let's look at the substances which are used in the mixtures. Substances are called pure substances. They are pure. One of them is elements. Elements have only one kind of atom. There are hundreds or 114 elements in the periodic table. They have definite atomic structure, unique atomic structure. Number of protons, neutrons are specific to each element. And atoms combine to make molecules. In a compound, there are more than two elements. In this diagram for compounds, the first one is water in a beaker. Water is a compound. Why? This is a mixture of, this is composed of, molecule composed of two hydrogen and oxygen. Salt shaker here, salt inside. Salt is sodium chloride. This is an ions compound created by sodium ions and chloride ions. That's why I call it atoms, molecules, and ions. So you get the idea. Elements have only one kind of atom. Molecules have more than two types of atoms. Mixtures are made from substances, pure substances or substances. They are a mixture of two elements or mixture of element and a molecule, element and a compound, or mixture of two compounds, etc. Mixtures have more than one pure substance. So they could be heterogeneous and homogeneous mixtures. Mixtures are mixtures of elements with elements or elements with another compound or two different compounds, more than two, to qualify for a mixture. So homogeneous is composition is same throughout the sample. On the first example right here. Composition is same throughout. Heterogeneous is composition is not same. There are different phases, different parts of the sample, different composition, therefore heterogeneous. We're going to talk about this little bit more than now you understood atoms, molecular science make the matter. Simplest matters is substances, elements, and compounds. The complex matter is mixture of elements, compounds, more than one of them. Elements. Mixtures could also be heterogeneous or homogeneous depending on the distribution of mixture in the sample. Do you have any questions? Are you guys?
No, sir. No, sir.
Okay. I'm just checking. Now, as I told you before, substances we call pure substances. One of them is elements, which are made out of one kind of atom. Aluminum is the atomic symbol for aluminum is Al. A sample that contain only this pure substance of aluminum. They have constant composition because there's only one kind of atom. The atoms cannot be broken down chemically. Therefore, this is the smallest particle of matter, atom. Element is a pure substance that cannot be broken down by chemical change. Nuclear change you can break down, but we don't do nuclear chemistry. This is chemistry, regular. Atoms and molecules are conserved. Atoms are conserved. Second part of pure substance is compound. We talk about water and sodium chloride. This is a sodium chloride. It's made out of two kinds of atoms which are in the ionic form, sodium ions and chloride ion. When they form the compound, sodium ion loses electron, give it to chlorine become chloride ion. So they are in a heterogeneous mixture, homogeneous mixture. Homogeneous means it's distributed. Therefore, any pure substance is homogeneous. Elements or composition is, but mixtures could be heterogeneous and homogeneous. Now we're going to revisit three states of matter from the point of view of states: gas, liquid, and solid. So the structure of the atoms and molecules decide the gaseous state. This is an example of water. We only look at gas, liquid as a experience. We can tell gas, we cannot see the gas, but liquid we can see it in a beaker. Solid we can. So even though we cannot see a gas, there are particles of water in the gas. So it has no definite shape. It expands to the container. So depending on the physical state of the matter, properties are different. Liquid state has definite volume, takes the shape of the container. Now they are particles of water molecules are close together, attracted to each other. Therefore, they can roll over. Okay, in the solid state, there's a definite shape. It maintains the shape regardless of the container. Solid particles of water molecules are close together. They are strongly held. So that's the description of states. Now, all these pure substances, just like water or sodium chloride, compounds, elements, and water is a compound. Either compound or elements have physical properties. Their physical properties depend on the states, boiling point. If something has a higher boiling point, that's normally present in liquid and as solids. Low boiling point, low boiling point also present in gases. Solubility is another criteria as a physical property. Solubility is soluble in water or insoluble in water. Pure substances also have physical properties. One of the is color. They also have an odor. You can, if it get into your nose, you can smell. There's a definite state of matter. Water is liquid. Melting point and boiling point values are dependent on physical state. Normally at room temperature, something is liquid, means they have a higher boiling point or lower freezing point, like that. So physical property of a matter, which are elements, compound, and mixtures. Mixtures are different issue. They don't have physical properties, constant physical properties. Mixtures have different properties depending on the component substances in the mixture. Therefore, physical properties are important for elements and compounds. A chemical property is something that shows reactivity of substances, atoms or molecules or compounds. It describes reactivity towards oxygen, combustion. For example, if you have hydrogen and oxygen mixture, as in this picture, hydrogen here, yellow, that gray balls, and oxygen in the red balls, two oxygen atoms, two hydrogen. When you react with them, when you put them together and ignite, they turn into water. So combustibility of hydrogen is a chemical property. Therefore, many different substances have certain chemical property. Some doesn't combust. Some rust. Rust is another reaction where oxygen is combined with iron to make red colored iron oxide. That's a chemical property. So density is one of the physical properties of matter. Density is defined as mass of an object divided by volume. So you measure mass of an object and get the number, measurement in grams, and volume is in milliliters, as in this example. 73.2 milliliters of a liquid has a mass of 61.15. The 61.5 divided by 73.2 get the density. Now, when you do the calculation, there are 3 significant digits in both. So therefore, this should be rounded up to 8.840. So density is calculated by dividing mass or volume by volume. Density could be used to calculate. If you knew the volume of a sample, if you knew the density, you can get the grams using the conversion factor, which is the density. If you knew the grams, you can get the milliliters of sample using the flip side of grams here to cancel out. This is like a conversion factor. So sometimes this conversion factor that comes from a measurement is not exact. Density is not exact. Density has an uncertainty. 1 milliliter here is exact number. 1 is exact. Therefore, you have to consider uncertainty in the grams and milliliters when you're calculating the mass or the milliliters. One another way to express density is specific gravity. You can obtain specific gravity of a sample of a piece of substance, object. Density divided by density of water. Density of water is 1 gram per milliliter, 1. Therefore, the denominator when you calculate specific gravity is equal to 1 water. When you get the density divided by 1, the units cancel off. Therefore, specific gravity is unitless. And we use this directly. If something has higher number, specific gravity is high number, that has a higher density. So therefore, we interchangeably use specific gravity and density as properties. So a lot of places we use specific gravity also. That's why we show you what that is. How do you calculate specific gravity for copper? Its density is 8.92. Water is 1.0 grams per milliliter. So the answer is 8.92. I'm going to stop at this point, okay? You guys there?
Yes, sir.
We will meet on Tuesday, okay?
Okay.
Have a great weekend and just get ready for classes next week. I know you've been moving around in the campus trying to get signatures and things like that. Okay?
Okay.
Okay. Did you sign the chat box? Yeah, I see you have. All right then.
Mm,
See you next week. Okay?
okay.
Thank you.
Take care. Bye-bye.
Mm.